The important means are pratyaksha, which is perception. That is the most important source of knowledge. Then anumana, which is inference. Then upamana, this is comparison, acquiring knowledge by comparison. Shabda is by verbal testimony from an authentic source. Arthapatti from postulation. Anupalabdhi from non-perception. Absence of something may indicate some information which is obtained from anupalabdhi. So just repeating these terms again, they have, we see their relevance in today's world of LLMs. Pratyaksh, Anuman, Upaman, Shabda, Arthapatti, and Anupalabdhi. Then we did two mathematically interesting and fundamental discussions, which was central limit theorem and also law of large numbers. So law of large numbers can be formally proved by Chebyshev inequality, Markov inequality, and so on. And CLT also can be proved by making use of unification theorem and moment generating functions. Okay, so these are foundations of probability theory, and they are very much relevant wherever we make use of probability as a conceptual framework. Okay, and NLP needs lots of probability, as you have been seeing now. Now, an important point from this for next semester's course, which is deep learning for NLP. So their concepts will be re-examined from the point of view of implementation, where the machine is a neural network. And since probability and NLP are going together, as you see, we need an important discussion on how is probability implemented in neural network. Okay, what is the mechanism to implement probability? That mechanism is softmax. Okay, so softmax links a neural network with probability. Let us remember that more about this next semester. So central limit theorem and law of large numbers. Central limit theorem says that the sum of random variables whose mean and standard deviation are given, they have identical mean and standard deviation. The sum also is normally distributed. Okay, and the mean of that normal distribution is sum of the means, and the variance of that normal distribution is sum of the variances. So this is the non-trivial and the most interesting part. Okay, this, I don't know if it is something you anticipated. That is the theorem part, and the proof also is very interesting. Proof depends on moment generating function and unification theorem. Unification theorem states that the two probability distributions are identical if and only if. It is a two-way equivalence. If and only if their moment generating functions are equal. Okay, so these were made use of. Then we started dependency parsing. Very quickly, the dependency parsing also makes use of part of speech tags, because you need to know nouns, verbs, adjectives, adverbs, and so on. And in dependency parsing or any kind of parsing, the key concept is head and modifier. Okay, if I take a pair of language objects from a sentence, which language object is head, which is modifier? Not that all pairs are head modifier related, that we know, right? But this pair of words need to be identified. That is the most important task in dependency parsing. And then we have to give labels to these relations. That is the other part of the story, which is also very important. So all these are classification decisions, which is why machine learning and NLP are so closely integrated. All the time we are making classification decision. You have seen in part of speech tagging, you are taking classification decision. You are doing support vector machine-based named entity identification. Again, classification decision, right? 1-0 decision. So this is the way it goes. In dependency parsing, the first classification decision is how to find the root main verb. Okay, I keep looking at every position and ask, is this the main verb? And that search can be reduced if we concentrate only on verb, ignore all the non-verb part of speech tags. And then the next classification question is between the pair of words, which is the root and which is the modifier. And having found the root modifier, what is the relationship that applies? So this is the way we have gone, and this was a very fundamental discussion that the syntax can be deceptive. Okay, the syntax can have the same relationship called n sub nominal subject, but the underlying relationship, which is deep semantic relationship, that need not be identical. So here you see agent, instrument, object, time, place. All of them have the syntactic relationship of n sub on the dependency parsing graph. And the translation reveals that these relationships are different. Okay. So we went through these labels uh, in the last class, that is yesterday, and I said that these labels are created by deep insight into linguistics and also into machine learning. Okay, this is something we discussed yesterday night. And there were linguistic intricacies, for example, C-comp and X-comp. These two relations are created, even though the meaning is same. I said that he should go. I told him to go. These two relationships are always between the main verb and the subordinate verb. Okay, these relations are always between two verbs. One verb is main verb, the other is clausal verb, and we need two different relations for this. Okay, that is because of some linguistic intricacy, which is finite verb and non-finite verb. So you would have marked them. Then all kinds of modifiers are required. Then we started projectivity. This discussion I would like to repeat a bit. I don't know if all of you are present yesterday. And this is a very elegant concept. So we want our dependency trees to be projective. Now, dependency tree is composed of different arcs. It's a tree, so every node has at most one parent. So an arc from a head to a modifier is said to be projective if there is a path from the head to every word that lies between the head and the modifier in the sentence. This is the foolproof definition of projectivity, and it has implication for dependency algorithms. A dependency tree is said to be projective if all the arcs that make it up are projective. Okay, the tree is projective if all the arcs inside the tree are projective, and the arc is said to be projective if there is a path from the head to every word that lies between the head and the modifier. And there is another equivalent definition of projectivity, which is that all the arcs should be drawable either on the upper part of the sentence, upper half of the sentence, or on the lower half. So this sentence, if you look at, JetBlue cancelled our flight, which was late. The core sentence is JetBlue cancelled flight. Okay, so it is always very useful to look at the kernel of the sentence, the core of the sentence. The core of the sentence is always subject, verb, object for SVO class of languages. So JetBlue cancelled flight is the core sentence. Then cancelled is the main verb. From cancelled, we see an n sub relation to JetBlue and OBJ relationship to flight. From flight to hour, there is another relation, which is DET, determiner. Which flight? Our flight. And since cancelled is the main verb, the root node sends the arc directly to the main verb. So this is the core sentence. Then there is a clause, which was late. So there is a convention. There are many different conventions of linking the main sentence with the clausal sentence. One of the conventions is shown here. So you see, you think a bit deeply on this point. The clause comes as a modifier for a noun. Okay, clause comes as a modifier for the noun. And the difference between clause and phrase is that clauses have their independent verb. Okay, so which was late, in that you have an independent verb was. So this clause, when it comes as a modifier to the flight, we follow the dependency principle. The dependency principle is that the most important entity in a sentence is the main verb. Okay, so the main verb provides the stage on which noun phrases operate as actors. Okay, so which was late is the clause, and since it is also a kind of a sentence, the main entity here is was. So the noun which is modified by the clause, we say, is actually modified by the verb of the clause. Okay. What is the other mm, other framework? What is the alternative framework? The alternative framework is that the word flight is modified by a relative pronoun, which is which. Okay. So this is a very old debate, old tussle between verb-centric representation and noun-centric representation. This is a very old linguistic question, philosophical question. What is more important in a sentence, noun or verb? Okay. Information retrieval era said that nouns are most important because they carry the information load. Whenever we retrieve pages, documents, etc., they are triggered by the noun. But the semantics, meaning, question answering, sentiment analysis, inferencing, they say that no, the verb is most important. Okay, it is around the verb that all other entities in the sentence, noun phrases, nouns, they gather around the verb. Okay, by different relationships. So, following that philosophy, we link the noun with the main verb of the sentence, of the clause. You must remember that the alternative is to link the relative pronoun with the noun. Now, there is a little bit of complexity there. Sometimes the relative pronoun is dropped. Okay. Uh, the boy whom I saw yesterday lives in Delhi. The boy whom I saw yesterday lives in Delhi. So do you see that the relative pronoun can be dropped? The whom is it necessary? The boy I saw yesterday lives in Delhi. So whom is not necessary. So English language allows dropping of relative pronoun in this case. When that happens, what do you do? What will you link the noun with? It is not there in the sentence. It is implicitly there, but not on the surface. So that's why this seems like a more foolproof procedure where we link the main verb. And the main verb is linked by the relation ACL, clausal modifier of noun. CL, I think, is clause. I'll have to see what it means. And WP is the relative pronoun. So I hope you have appreciated this debate of what to link with the noun which is modified by a clause, relative pronoun or the main verb. Okay, so in this case, you see all the arcs are drawn on one side of the sentence on the upper part, and there is no crossing of arc. No arc is crossing another arc. But if the sentence is modified to JetBlue cancelled our flight this morning, which was late. So here, what has happened is that the modifier and the modified, that is the head, they are not adjacent to each other. Whenever this happens, there is violation of projectivity. And if the question is, what problem does it cause? The problem that it causes is that a very simple and elegant dependency parsing algorithm called transition-based parsing fails in such case. Okay, that is the problem. And also it can lead to ambiguity. It can also lead to complexity of absorbing the meaning of the sentence. So here, when I draw the dependency arcs, you see there is a crossing of arcs. Okay, the OBL is crossing the ACL arc. JetBlue cancelled our flight this morning, which was late. Okay. Now, what about this definition of finding a path from the head to every intervening word between the head and the modifier? So you see there is an arc from flight to was. Intervening word is which. Is there a path? Yes. Flight to was to which. Then if I consider this test for this particular dependency tree, and if I take the arc from cancelled to morning, intervening words are our, flight, this. So cancel to morning, I have the path. Cancel to morning to this, I have a path from cancel to this. Do I have a path from cancel to flight? There is. And cancel to hour? Yes, there is. So there is no projectivity violation there. But for the other arc, which is going from flight to was, you see there is no path from flight to morning. And consequently, there is no path from flight to this. So this is an equivalent definition, not equivalent, this is the main definition of projectivity. And the consequence of this is that if I draw all the arcs on one side of the sentence, there is no crossing over, and all the and also there is no crossing of arc, of course. So this is the definition of projectivity. Now let's see how the projectivity can be restored. JetBlue cancelled our flight, which was late this morning. If I shift the preposition phrase this morning to the end, then projectivity is restored. If we shift this morning to the beginning, which English allows, this morning JetBlue cancelled our flight, which was late, then again projectivity is restored. Okay, there is no crossing of paths. So this movement of the adjunct, like a preposition phrase from one part of the sentence to another part, that is much more possible in English. Okay? For example, in Hindi, you will not be able to push this morning to the end of the sentence. It can come in the beginning, in the middle of the sentence, but never to the end of the sentence. Okay. Yeah. Come again. Yes. Yes. Correct. And the linguistic principle is that head, there should not be any textual separation between head and the modifier. Now you see, let me do a bit of digression. Whenever a head and modifier are not adjacent, it produces cognitive load in our processing. This has been verified by reading studies, making use of what is called an eye tracking machine. We have an eye tracker in our lab. So you will see that when a person is reading the first sentence, then the eye will smoothly make movement forward. This is called progression. Then, so then when it hits this morning, maybe it will progress again, which was late. There the eye will wait for some time. This is called fixation. And fixation is easily seen from the eye tracking machine. You will see a ball, large ball, on the word where the eye was resting. The more time it spends on that word, the larger is the radius of the ball. Okay. Now, what is the cognitive load here? JetBlue cancelled our flight this morning, smooth flow, no problem. Which was late. Now, when I hit which, I know that which is a relative pronoun, it binds to some noun. But there are, how many candidate nouns are there? There is JetBlue, which is a noun. Flight is a noun. Morning is a noun. Now I have to conduct a search. Which of these nouns can be bound to which? Okay, that causes the cognitive load. It is verified by eye tracking machine also. Let me give you another sentence, which was our object of study for quite some time. So let's say with some violation of syntax, John is in market. Okay, John is in the market. Okay, John is in the market. Let a person do some reading, do a reading, and let's study his cognitive load. John is in the market. Fine. And the other sentence, which is similar structure, syntactical structure. John is in a soup. So John is in a soup is a metaphorical sentence. We have seen through our eye tracking machine that the eye rests for some time on soup. What did I see? How can somebody be in a soup? So you have to invoke your metaphorical faculty, metaphor processing faculty, and then understand that John is in a difficult situation. And therefore, we have a paper in ACL which says that one should never pay the translators by the length of the sentence. Typically, the payment to translators is, some 2 rupees per word or 10 rupees per word, and so on. But both these sentences have same length, and the payment will be same. But that's not fair. The second sentence needs much more processing, and the cognitive load is higher there. So this we had shown using eye tracking. So in dependency parsing also, the eye tracking study shows that head modifier separation increases cognitive load. Remember this when you write your MTP report, seminar report, and papers and so on. Always place the modifier and head adjacent to each other as far as possible. Yeah, this is a good hint for writing. Okay. This is a bit subtle. The athlete runs fast who also jumps high. So here the adjacency violation has happened. The athlete runs fast who also jumps high. You can restore projectivity by bringing who also jumps high adjacent to the athlete. The athlete who also jumps high runs fast. And there you can see in the second sentence, there is no crossing of arc. But in the first sentence, there is crossing of arc. I remember in last year or year before last, a student said that just reduce the length of this root arc. Okay, then there is no crossing of arc. But I don't know what to say. I cannot argue against this, but you have to extend the arc and see that there is crossing. Okay, now projectivity also holds for all languages. This is a very universal phenomenon. JBL ने हमारा फ्लाइट को रद्द किया जो लेट था. जो late था is a modifier, and this is a modifier for flight. Between head, flight, and जो late था modifier, there is text, रद्द किया. And therefore, there is crossing of arc. And if we apply the other projectivity test, which is path to all the intervening words, that will also fail here. You can restore projectivity by saying, JBL ने हमारा फ्लाइट को जो लेट था रद्द किया. Then projectivity is restored. Okay, and projectivity is universal across language and has been extensively studied. Okay, now let's go to algorithmic aspects of dependency parsing. Dependency parsing is essentially shift reduce. I can best explain this through an example. The sentence is, I spotted you with binoculars. You know that this sentence is ambiguous, right? Who has the binoculars is not clear. So I spotted you with binoculars. Now, tell me quickly, if I have the binocular, then the dependency arc, one particular dependency arc will be different from the sentence where you have the binocular. What is that dependency arc? One going from binocular. Eye to binocular, there will not be any arc. If I have the binocular, then there will be an arc from spotted to binocular. Okay, binocular being the instrument. And if you have the binocular, then there will be an arc from binocular to you. You with binoculars, a special you who has binocular. So I spotted you with binoculars. Notice the index between the words 0 before the sentence, then 1, 2, 3, etc. between the words. It has two meanings. I have the binocular or you have the binocular. The unlabeled dependency tree will be as follows. So the transition-based parsing, which we're going to describe now, will be for unlabeled dependency tree. Unlabeled dependency tree does not worry about what label to place. So it first solves an easier problem. So you see from spotted, look at the direction of arrows, spotted to I, then spotted to U, core sentence, I spotted you. Then spotted to with, then with to binocular. The other dependency parse is spotted to I, spotted to U, then U to with to binoculars. So this shows that with binoculars is attached to you. That means you have the binocular. Okay. So now this sentence should have two parse trees when we run the algorithm. With labeling, spotted to I is n subj, nominal subject. Spotted to U is direct object, DOBJ. Spotted to with is mod, modifier. With to binocular is POBJ, preposition object. And that's all. In the other case, spotted to I and sub spotted to U, DOBJ. U to with mod, with to binoculars, POBJ. These two trees should be produced. Now let's look at the, an interesting thing. So, very interesting thing. So for languages which are SOV, where the main verb goes to the end, it's very interesting that all arcs, all dependency arcs, have to be left pointing. Okay, all the arcs from the main verb will be left pointing because the verb goes to the end. In English, where the verb is between subject and object, the arcs can be left pointing or right pointing for the main verb. Okay. So you can see that one classification decision will be whether to place a right arc or a left arc. This is also a classification decision. Look at the first parse tree and the processing. So there is a data structure where, first of all, I have root, okay, between two square brackets. Then I have the full sentence, which is the second component of the data structure. I spotted you with binoculars. And then there is a third element in the data structure, which specifies the action taken. And then a comment, no relation needed, etc., etc. So let's look at the processing. Root, I spotted you with binoculars. Now root will have to link with something. It has to link with the main verb. So I shift I. So I shift I, leaving spotted you with binoculars on the stack. Okay, I has been shifted. And the operation is shift, as you see in the first row. Now, the question is, should root be linking to I? So this is a yes-no decision, and you need a classifier, which is either rule-based or trained, a machine learning model which is trained. So now the decision has been to shift again. A classifier is run. So I shifted again, second row. Spotted has come to the first part of the data structure, root, I, and spotted. Exposing you with binoculars. Now, the classifier tells me, you can look upon this as an oracle. Classifier tells me, take the action of placing left arc. So spotted to I, there is a left arc. So you can see that in the last column, spotted to I, left arc has been created. And when you do so, the modifier goes out of the stack. Okay, head has to remain. So spotted remains, and I has gone out of the first component of the data structure. This is called transition-based dependency parsing. We'll very soon see why it is called transition-based dependency parsing. So U is there. Now two things could have been done. I know there is a very high demand for spotted to be linked with root, but there is a timing for everything. This is not the right time to link root to spotted because spotted is modifier, head is root. From the root, the arc goes to spotted. The algorithm is such that the modifier leaves the first component of the data structure, goes out of reckoning for further processing. If the main verb is gone, then what will happen to the rest of the words in the sentence? Right? So you can see that the main verb has to exit the processing data structure quite late. After linking all the modifiers and after linking with root, it has to go out of reckoning. So spotted U has been shifted. There was a shift action there. Note this very carefully. And in your mind, see that it is classifier all the time. You are getting decision from the classifier. If it is a probabilistic classifier, then the highest probability action will win. How many actions do you see in front of you? Shift, left arc, right arc. Just 3 actions. So there will be 3 class classifier. If it is a neural network-based classifier, there will be 3 neurons with softmax operation. If it is a transformer, a feed-forward layer at the top with 3 neurons, giving the probability. If it is a large language model, you don't have to do anything. The large language model just fine-tune. Fine-tune with what? We'll see the data. Okay. So now, through shifting, U has come in the 5th step. This pointer actually doesn't point to the screen somehow. I don't know how to solve this problem. It points here, but never inside the screen. Now, U has been shifted, 5th line, and with binoculars is exposed. Now, right arc operation is done, and spotted to U, a relationship is established. What goes out of the reckoning now? U. The modifier always goes out. Remember that modifier goes out. Then with binoculars is exposed, with is exposed. So with comes to the 7th row, 7th line, with comes in, and spotted and with are adjacent to each other. Binoculars is in the other stack. With binoculars, I can create a right arc. Right arc. So with and binoculars are linked. With binoculars is also shifted. Sorry, 8th line, binoculars also is shifted. So with binoculars is linked. Binocular is the modifier for the preposition phrase. Goes out. With remains. Then the 9th row, spotted with. You create a right arc from spotted to with. The moment I create a right arc from spotted to with, I'm committing that I have the binocular. Otherwise, this with would have gone out of the stacks much earlier. Now we have root and spotted. Create a right arc from root to spotted. Spotted goes out. Root only root remains. In the beginning also there was only root, but the second component of the data structure was full with all the words. Now the second component is empty. Root remains, and the parsing ends with success. So this is called transition-based parsing because the whole machine transits from one state to another. Those of you who have done Turing machine computation would relate to this. Okay, there is a state in which the machine exists. Then the operation of shift, left arc, right arc takes the machine to a different state. In the state, there are 3 components. Actually, most importantly, 2 components. The first stack and the second stack. Okay, it's clear. Now let's compare the operation with parse second parse. Again, root, and I spotted you with binoculars. first operation has to be shift, line number 1. So I comes into the first stack. Spotted U with binoculars, like before, spotted also gets shifted. U with binoculars, now there is a left arc from spotted to I, and subject has been found. Spotted U. Spotted U. U has come to the first stack. Now, last time we created an object relationship from spotted to U, and U had gone out of the stack. But in this case, I shift more. Compare the fifth line of parse tree 1 and fifth line of parse tree 2. In fifth line, right arc. In fifth line for parse tree 2, shift. Okay. So between right arc and shift, I have chosen fifth for the first parse tree. For the second parse tree. And for the first parse tree, I chose right arc. Why? Guided by the classifier. And if I need both the parse trees, then of course both operations will be executed, and I'll follow two different computations. So now U did not get resolved. So I shift and I bring in with line number 6. Then I shift binocular, line number 7. Then right arc from with to binocular. And then line number 8, U to with. The moment I link U to with, and with was already linked with binocular, you have the binocular. Then with goes out. Spotted U remains now. Spotted and U are linked with right arc. How late the U is exiting, you see? The word U exited very early in the first part. In the second part, U is exiting very late. And then root and spotted, finally root. So the algorithm is clear to you. Very elegant algorithm. It is totally controlled by these classification decisions. Very similar to push-down automata computation, Turing machine computation. Any question? Okay. Now let's look at some classifier rules. Some of the rules are very obvious. You will be able to suggest it. What is the first rule for shifting? It will be a very simple rule. First rule. Yeah. So no arc placement is possible. So shift. There is no other choice. Then second line, root and I. Why shift? What kind of rule is operating? The rule could be I is looking for a head. I is looking for a head. So head could be root, but the timing is not right. Not at this time. So I is eager to become the modifier of a head. Root exists, a possible head, but it will lead to a lot of problems. I will go out and the parse tree will be wrong. So a rule which you can think of is that I is looking for the main verb. I can be linked to a verb. Where is the verb? And verb will come from the features of the word. One of the features is part of speech tag. You see the importance of part of speech tagging. It is used everywhere. Okay, so this way the rules will be operating, and indeed in the early period of dependency parsing, this kind of rules were created quite painstakingly. And rules have the problem that there can be conflict of rules. Rules may not cover all possibilities. Rules can be inconsistent. Okay, all rule-based systems have this problem. So then it shifted to data-driven algorithm. So let's have some discussions. Essence of dependency parsing: cannot pop a head out of the stack if any of the dependents remains on the stack. The above works if the sentence's semantics is consistent with projectivity. So this is where the projectivity plays its role. This constraint of not popping the head until all its head modifiers are over tells you the importance of the projectivity rule. Remember, there has to be a path from the head to all the intervening words between head and modifier. This exactly corresponds to this rule. Okay, all the modifiers have to be out of the stack, and then only the head can be removed. This is a consequence of projectivity. Think about it. Then there is a CYK algorithm, CYK-like algorithm for dependency parsing, which is why I said CYK is so fundamental to the whole NLP. So the gunman sprayed the building with bullets. First of all, I have the rows and the columns as is required for CYK parsing. So between the and gunman, I will place an L. Okay, because gunman is the head and the is modifier. So there is a left arc from gunman to the. Then between gunman and sprayed, again a left arc, L. From the main verb, I have N sub relation to gunman. Then between the and building, again an L. Between sprayed and building, R, right arc. Then between with and bullet, R relation, with and bullet. Then between spread and with, sprayed and with, R relation. All these essentially transition-based parts. Okay, so it is non-trivial to create this classifier, which will give the correct decision at every step. Okay. Also, since there is ambiguity and you can have multiple parses, you have to both parses or multiple parses are valid. You have to have a decision to prefer one parse over other. So preferring one parse over other is always dictated by maximum likelihood, almost always. If there is no other consideration, and maximum likelihood is a probability, essentially probability. So what do we need for training a classifier? The fact that you need classifier at every step, I think, is obvious to you now. Okay, right arc, left arc, shift. Three decisions you have to take. One of the three options you have to choose. Okay, so transition-based parsing we have seen. The other parsing is called graph-based parsing, and graph-based parsing is based on the maximum spanning tree algorithm. This I'll not be able to cover in this course. There will not be time. But in our book, Natural Language Processing by me and Aditya Joshi, there is a good intuitive discussion of graph-based parsing. So in basic transition-based parsing, there is the parser, there is an input buffer, which you saw. Okay, the flight from Calcutta to Mumbai, the whole phrase is on the input buffer. And the parser actually keeps consulting two adjacent nodes, two adjacent words in the stack, and creates the relationship or draws the arc, and then removes the modifier out of the stack. This is how the parsing proceeds. So dependency relations are also obtained from a repository. Now, those of you who are working on RAG, retrieval augmented generation, will notice that these dependency relations which are coming from a repository can come as a RAG resource. Okay, so dependency parsing is very well done by large language models. You simply need some fine-tuning data, small amount of fine tuning data, and the huge number of parameters in the large language model trained on a huge amount of dependency, huge amount of raw corpus is already empowered to absorb some amount of fine tuning data, which is dependency parse data, and is able to do dependency parsing very well. Okay, so here the dependency relations can be obtained from an external resource, or it is on the label data. So what I'm saying, just note, you can create unlabeled dependency parser by fine tuning, and the dependency label can come from an external source. Why should it come from an external source? Well, I do not have a lot of money to employ very highly skilled expert annotators. They can detect dependencies, but they cannot accurately give me the classification level. It is not easy to think of when to give CComp, when to give XComp, when to give NMod, when to give AMod. Okay, it requires some expertise. So if I don't have money to employ very highly skilled annotators and large number of annotators, let me at least get some dependency parts and rely on RAG, retrieval augmented generation, to get the dependency labels from an external source. Okay, that's always possible. So there is an oracle which decides whether to shift or to reduce. Reduce whether to set up a right arc or set up a left arc. Okay, reduce means an operation. It can be controlled by dependency grammar rules. So that's why dependency, we did not cover dependency grammar. So dependency grammar specifies a set of rules. You have a left-hand side of the rule and the right-hand side of the rule. Right-hand side replaces the left-hand side, and that replacement is controlled by the dependency grammar, or by rules learned from the data, or by a neural network. So here is a neural network which is shown here. And there was this paper in 2014 by Chen and Manning, which showed, I mentioned softmax layer. The softmax layer is on the top, you can see. And that decides which operation to do, shift or left arc or right arc. Okay, and the training is done by a neural network with non-linearities. So this is a topic for the next semester, of course. I apologize. But there is a classifier which can be trained this way. And amongst all the competing classifiers, neural networks have done very well in this particular case. How to get the neural net trained and how to get the training data? The training data will come from the dependency trees, which are already created. For example, given the morning flight, the flight, morning flight, these are the dependency arcs. It is possible to simulate the parser, generate the training data. So you can generate the training data synthetically by running the dependency parser, dependency grammar rules. Such trees come from Prague Dependency Tree Bank. And so the main source of data for dependency parsing is Prague Dependency Tree Bank. So English has all these resources. English is very resource rich. In India, we created some amount of dependency tree. For in Bombay, we created some amount of dependency tree for Marathi. Hindi was created in mainly in IIIT Hyderabad. Tamil was created in Anna University, KBC, and so on. Many different institutes were involved in this large nationwide project. But we did not create lots of dependency tree. But in the era of large language model, it is now possible, we see, to retrieve that small amount of data which was created and see if zero-shot, few-shot learning can be employed on this large language model. Some of the language models are multilingual, right? You know, like Muriel, for example, is for Indian languages. Indic BART is for Indian languages. But these are not large language models. These are language models. Okay, so we'll have to see how their performance is. But a very interesting possibility is to take, let's say, Mistral, these kind of large language models, or GPT-4, for example, and take this small amount of data, train it, and see. We can even prompt, okay, and see the result. So those will be nice discussions exercises next semester. Now let me go to a very important topic, very important topic in language processing. And this was a thorn in the flesh. Okay, this was a deceptive problem. It was not understood for a long time what was causing difficulties in machine translation. Named entities, proper nouns. Proper nouns are so important in language, but proper nouns are nouns. Okay, so treat them like nouns and be done with it. No. Nouns, which are proper nouns, they carry huge amount of semantics with them. Pragmatic semantics. If you hear the name Narendra Modi, okay, immediately the notion of prime ministership comes into mind. Hear the name Ram, does it come to your mind? No, I mean, if you are mythologically interested, then you'll think of Ram as God. But these names carry semantics with them. They have a lot of nuances. Those nuances have to be captured for question answering, information extraction, and so on. Also, it has been difficult to place named entities on the NLP stack. Okay, some people have said that do named entity recognition before pause tag. And the other school says no, first do part of speech tagging and then detect the names. What could be the reason? What would be your preference? Do pause tagging, then named entity, or named entity first and then pause tagging? Some of the answers is that languages which do not use capitalization or languages which do capitalization for all nouns. German, for example, uses capitalization for all nouns, common noun, proper noun, everything. English that way historically has been clever. The proper nouns start with a capital letter. In Indian languages, there is no capitalization. So Pooja ne Pooja ke liye फूल खरीदा. Which Pooja is proper noun and which Pooja is common noun? कमल कमल देखकर खुश हो गया. So proper noun, common noun ambiguity is very common, okay, in Indian languages, mainly because there is no proper noun, no capitalization. Even if there is capitalization, the common noun coming in front of the sentence will again be capitalized, right? Houses, houses were built. Here H is capital. So houses, is it somebody's name? Right? So this common noun, proper noun ambiguity is a problem. Another problem is that named entities can be multi-words. You can have a named entity or proper noun, name of an organization, for example, Indira Gandhi Open University. The whole thing is a name. Okay. So it will be very difficult to do named entity recognition without doing part of speech tagging first. So you should do part of speech tagging and then do named entity recognition. But then comes the problem of disambiguating named entity before part of speech tagging. Kamal Kamal dekhkar khush ho gaya. Which one is proper now? Kamal. And since this is pre-word order, you cannot rely on the position of the word. Kamal dekhkar Kamal khush ho gaya. Right. So that signal is not also not very reliable. But we operate with uncertainty and therefore we have to resort to probability. So in this case, the thinking is that named entity recognition is somewhere between chunking and pause tagging. For multi-word named entities, you'll have to do chunking, you have to group them together. And part of speech tagging is a good step to take because parts of speech are valuable signals for named entity recognition. So what is the ambiguity in named entity recognition? The first ambiguity is this noun a named entity or not? Named entity, by the way, is the name of an organization or a place or an artifact and so on. So first ambiguity is this noun a named entity or not? Second ambiguity is, what is the category of this named entity? Is it a person or a place? Washington voted Washington to power. Washington voted Washington to power. What is the meaning of this? People of Washington voted for George Washington and made him the president. So Washington is the name of a place. Washington, D.C. is also the name of a person. So it is most probably between chunking and pause tagging, but there are many theories on this. A lot of people place named entity as high as the semantics layer because named entities carry lots of semantics with them, pragmatics and semantics. And there is multilingual named entity recognition problem. Ultimately, we are interested in a piece of code and algorithm for the problem of named entity recognition. And it is heartening for us to know that first named entity recognition problem was attempted as a sequence labeling problem. Okay, give 1, 0, which is your third assignment. Give 1, 0 label. So there is, of course, inherent resilience in language for disambiguation. There's a lot of disambiguation signal which is inherent in the language. So Apple increased its laptop production. A very strong clue is coming from laptop. If you train a transformer, there will be a strong attention weight between Apple and laptop. I know that Apple increased its laptop production. Okay, fine. I know apples are costly, the fruit apple. And if there is no capitalization, it is the fruit apple. But I know apples are costly can also mean Apple devices, no? Loosely. Plural S is disambiguate. An apple a day keeps the doctor away. Article disambiguates. An apple. I bought an apple for my accounting work. Capital A is the disambiguation signal. But there can be vulnerability. He has an apple. Looseness in capitalization makes the disambiguation impossible. He has an apple. Okay. And if it is Indian language, उनके पास एक apple है, you do not know. It's impossible to disambiguate. In Bengali also, ওর কাছে একটা apple আছে. I think it will be impossible to disambiguate in any language unless there is some kind of case marking. Japanese, maybe not, because in Japanese, all nouns take a case marker depending on its semantic role. He has an apple. Will it remain ambiguous in Tamil? Tamil speakers? What is the Tamil? He has an apple. Clearly. What is the Tamil for he has an apple? Or some Tamil speaker? I want to see if there is any morphological disambiguation which happens. Apple as a fruit, apple as a device. Yeah. So what is the Tamil, Kannada, Telugu translation of this? उनके पास एक एप्पल है. सेब है. No, you can have food mixing. Yeah. So difficult, is it? So difficult to translate? No, no, no. Apple is a noun. No, sometimes morphological suffixes come. The target language puts no morphological suffix. Ram saw Sham, or I saw Ram. There is no morphological suffix in English, but ne comes in Hindi. Okay, so can that disambiguate? I was thinking. Okay, so there are disambiguation signals, right? Then multilingual named entity, a very attractive proposition is this. One of my PhD students, Rudramurthy, worked on this particular idea. If a named entity is recognized in one language, it can be added to lexicon. That lexicon is called the gazetteer list and can be used for processing tasks in other languages. So named entities typically don't change their form, except for some kind of morphological transformation. So Hyderabad remains Hyderabad in all languages, except maybe Telugu, where I was told that in a sentence it will be written like Hyderabadu, because in Telugu all words end in vowel. So some Telugu speaker can verify this. So extract once, use many times. That is the theme for multilingual named entity recognition. So named entity recognition has these approaches, very obvious. Supervised methods. In supervised methods, you can have graphical models. For graphical models, hidden Markov models have been used, but what has been very successful is conditional random field. Okay? So named entity recognition in a discriminative model has been more successful than generative model as a sequence labeling task. Deep neural networks also have been successful. Unsupervised, there you do only clustering. You cluster all the named entities, separate proper nouns from common nouns. Within proper nouns, you cluster all the place names. Okay, this you see happening in word vectors. Take the word vector of London, Paris, Brussels, Delhi, Mumbai. You will see that they form a cluster. Okay, so unsupervised methods essentially do clustering, as we know, and there are interesting pieces of work for clustering. Then semi-supervised method, there is this AdaBoost algorithm, which had become very famous. CLGN is an algorithm from our lab, which was published. And then hybrid methods. So statistical methods and rule-based methods working together. Semi-supervised methods, you take a little bit of data, annotated data, train a classifier, run it on some more unseen data, refine the labels manually after the classifier is given the labels, add it to the training data again, and increase the amount of training data, refine the machine learning model itself. This is semi-supervised method. Now, named entity recognition became important in the context of information extraction. Okay, to extract information that fits predefined schemas or templates. So, information extraction is a very important field of NLP, with probably the highest number of papers amongst all other areas. No, maybe competition is from machine translation. But after machine translation, you should see maximum number of papers in information extraction. In information extraction, we have to first and foremost detect an entity. Okay, Delhi is the capital of India. So Delhi, India, these are entities. Capital is also an entity. You have to detect them. Attribute, a property of an entity such as name and the type of the name, place, person, organization, and the relation, a relation that holds between two or more entities such as position of the person in a company. Bill is the CEO of so-and-so company. So you have some information extraction. Note the difference between named entity identification and named entity recognition. A named entity identification is what you are doing. It's a binary classification problem which classifies whether a given token is a named entity or not. And named entity recognition involves detection and categorization of named entities. So filling slots from text, this means you convert unstructured data to structured data. Unstructured data is running text. And use this to fill a table maybe. So given this text here, October 14, 2002, 4 a.m. Pacific time. For years, Microsoft Corporation CEO Bill Gates railed against the economic philosophy of open source software with Orwellian fervor, demanding its communal licensing, no, denouncing its communal licensing as a cancer that stifled technological innovation. So this was this very well-known war between um, open software and Microsoft's policy, where open software policy wanted everything to be open, and Bill Gates had opposed it for some time, saying that it will stifle innovation. If I do not have an incentive, if I can't make money out of the innovation, then where is the motivation? So these were two competing thoughts anyway. So we are filling slots. The slot template is pre-decided, name, title, and organization. So from this text, we have been able to identify that Bill Gates is the name, CEO is the title, organization is Microsoft. Then we can have an ad hoc relationship between Bill Gates and Microsoft, give it the level of CEO. Bill Bekte, Vice President of Microsoft. Richard Stallman was the big proponent of open source software from MIT. Title is founder and organization is Freesoft. You see, this way the table has been filled and unstructured data has been converted to structured data in the form of a table. So nowadays we have very nice tools and software. For example, Spacey is a software. OpenIE is another software which have been frequently used for doing this kind of information extraction and creating a table or table out of the unstructured data. More than table, the rows are very important. These are called knowledge tuples. And these tuples are converted into embeddings and fed into language models, neural network-based models. Very common. Okay. So before that, before getting this table, we have to get these tuples. These are called knowledge tuples. They are typically in the form of entity one relation entity two. And you apply some kind of vector algebra to create an embedding of this tuple from the embeddings of the constituents. We have some work in this area. So named entity identification, named entity recognition. NERC, named entity recognition and classification, involves identification of proper names in text and classification into a set of predefined categories, such as person names, organization names, location names, and miscellaneous names. Date, time, number, percentage, monetary expression, these are all named entities. They're all grouped under named entities. So when I say that the named entities invoke nuances, semantics, pragmatics in our mind, this is true. When you hear the named entity or the numerical named entity, 1947, other nuances come to your mind. 1947 has a special significance. 15th August, special significance. 26th January, special significance. Your own birthday, special significance. So they invoke semantics. So predominant named entity categories are person, organization, location, and miscellaneous. And there is a nice tree which I would like to show today and finish. And the data set. Yes. So named entity types have two predominant categories, enamex, numex, and timex. Time entities, they also contain dates. Numex is numbers, 15 kg, 23 miles. And enamex is everything else, person, organization, location, and so on. Okay, so we'll spend some time on this very fundamental and important topic of NLP. Large language models are doing an excellent job of this, but there are lots of very interesting concepts associated with named entity. And your assignment should give you some insight into the problem.